Hello, everyone. Welcome to the MTL Seminar Series. So today we invited Ashish to present Xilinx DNN processor. Ashish is a fellow engineer at Xilinx. He is doing exciting work designing, defining, and implementing both the algorithm and hardware and software architectures for accelerators for both deep learning, data analytics, computer vision, video codecs on Xilinx FPGAs. So if you're interested to learn more about deep learning and computer architecture, especially architecture for FPGAs with deep learning, you will enjoy this talk. So let's welcome Ashish to give us a talk.
Thank you. Hello. Can you hear me fine? OK. So thank you, Professor An, for introducing me. And I'm glad to be here. And my background is primarily electronic design automation. I have been doing electronic design automation tools for FPGAs for more than 20 years. And if you have done any FPGA design on Xilinx, Altera, Actel, you might have used RTL synthesis done by me or my group. So last 2 years, last 2.5 years, basically, we started looking into heterogeneous computing. And just because there is a need, I won't go into Moore's law and all those things. But fundamentally, there is a need. Market is driving it. And FPGAs, as always, have a potential of doing it. And what we started to look at it is, can we develop methodologies, examples, use cases, where people can really look at FPGA device as one of the viable heterogeneous device in the cloud as well as on the embedded world. Okay. So with this, deep learning is one of the hottest area. If you do anything in deep learning, people pay attention. But I think it is also a good area because just from the point of view of the problems they are trying to solve are kind of interesting. And what we really started to look into is, OK, can we do something on deep learning? Because every time people talk about FPGAs, FPGAs are great, they are programmable. But one thing which keeps on happening is they're difficult to program. Okay? And if you really look at the deep learning world, there are a lot of people who come from Python, from higher level of abstraction. And on the CPU and GPU world, that problem has been solved. They really don't have to go to lower level nitty-gritty. NVIDIA provides, as well as Intel provides, a pretty broad set of deep learning libraries where you can use. You can come at a higher level, do your work, and get out. And this particular project, we tried to address that problem. And to address that problem, we basically went through some of the looked into FPGAs in a very different way. And that is something I'm going to share. What are the lower level building blocks we used? How did we use? And I'll give you some pointers over here, which you can go and read. So before we go there, I think very first thing we realized around 2.5 years back is if we have to make people do anything on FPGA, they need to have ready-to-use boards. Okay? And we had variety of boards available for some time. But this year, we released our LVO series. And really, there are two versions of the board currently, U200. And just look at it from the point of view of it has around 1 million lookup tables. And U250, it has around 1.3 million lookup tables. And I'll come to lookup tables briefly. Some of you may or may not know about lookup tables. And there are other interesting things which are there is there's a lot of on-chip RAM. And I think as we will go and talk about developing an inference engine, you will see that on-chip RAM plays a very important property. As well as, there is a lot of bandwidth. When you're on the device, there's a lot of bandwidth. So you can move data in and out. You can move data between variety of your compute unit relatively easily. And these are some of the numbers we got on the CNN throughput. And I'll go over it in detail a little later. Now, just not like getting a board. Not everyone is going to buy this expensive board for $5,000, put it in the lab. We are also widely available on the cloud. So we released Amazon F1 instance last year. If you are interested in FPGA design, you can spin an Amazon F1 instance today and start doing an FPGA design. As well as in China, AliCloud and Huawei recently announced availability of FPGA on the cloud. China, if you really look for FPGA, China is where there's a lot of interest in FPGA. And then, Nimbix is one of the small private cloud, because many times when we release something on the cloud, Amazon has a process, and they may not want you to do everything. So Nimbix is another smaller cloud company where our both of the devices are available. And actually, Nimbix, at least I know, and Amazon through affiliation to MIT, you can probably get enough free credits to experience what we have over there. Also, from the point of view of server systems, now this particular solution works with Intel CPUs, Xeon, AMD, ARM multi-core or ARM server CPUs, as well as Power 9. So from that point of view, or from the point of view of ecosystem, you can get boards now. You can go on the cloud. And some of the things I'm going to talk about, you can go and try it out yourself. Now, when we think of heterogeneous computing, Xilinx basically thinks of network-attached acceleration. So typically, when you really think of accelerated computing from the GPU world, typically you have a PCIe attached to a Xeon processor. You'll offload your compute to the your accelerator. It will do the acceleration and give you back the result. But really, there are some very interesting properties you have. If you don't have to go to the CPU, if you can do your compute directly on the network. And the research from Microsoft has shown is you can really now implement a high-performance data flow programming paradigm, assuming you have many of these cards. And assuming these cards, given that these cards are available on the cloud, there is nothing stopping you from connecting hundreds of these cards and really do an unrolled data flow implementation of some of the algorithms. So for us, this is very important. Like, I don't think I'll use this. This is better. So going from the PCIe, not just focus on compute offload, but network offload and storage offload. Both of them are very important to us. But also, getting data directly from network or directly from disk, NVMe or SSD devices is also very important to us. And the way we are setting up our heterogeneous platform is to not just address the PCI attached compute accelerate, but also network attached compute accelerate. And we are spending a lot of effort, because at the end of the day, most of the users will really work at the higher level. And we are providing enough proof points or enough examples so that for different kind of applications like genomics, or let us say machine learning, or for that matter video codec, you can start from the very high level and go all the way down. And we provide a pretty good development environment. If you are really interested in accelerating compute or accelerating data center using this data center big cards, you go through SDXL. Or if you are interested just in embedded, you go with SDSoC. And we also support P4 and SDNet if you are interested in network compute, right? So overall, I think this is just something I wanted to share is a lot of work we are doing is not just enabling deep learning, but basically enabling deep learning in a more pervasive way, which is beyond PCI attached acceleration. So why deep learning is good or will work on Xilinx devices? So there are 4 properties, we think, which can allow us to build high-performance compute for deep learning. Number 1 is data parallel, and I'll go over, we have this inbuilt DSP block. And again, when I'm talking about deep learning over here, I want to clarify that we are primarily talking about inference. The model has been trained on GPU. This is for deployment on a large scale with variety of properties you want to have, like you want to maybe optimize latency, you may want to optimize, let us say, power, or you may want to mix and match with different workload. You can read the data from the input. So the focus is on inference. And the thing is that this data parallel architecture, which is more spatial in nature, allows you to connect your compute and memory in a very interesting way. So that's one very important thing. Other is custom memory hierarchy. I did indicate to you that we have a lot of on-chip memory. And that on-chip memory, along with your ability to build custom memory controller architectures, you can basically kind of have a very customized memory hierarchy, which is suited to how we are going to implement your application. Then compression and sparsity. And thanks to Professor Songhan's work, he has popularized this, that in the deep learning, when you are doing inference, even though you will train your model in floating point 32 or floating point 16, when you have to deploy, int 8 is no-brainer anymore, but you can go below int 8 also. Now the thing is that is, just look at it from the point of view of hardware design cycle, right? Let us say someone comes up and say that I can do an algorithm with int 3 very well, right? Now you have to really spin off a new ASIC to really do it. It takes 18 months, right? But really on the FPGA, you could really try out all of these things, build your prototype, and maybe use it for production, or maybe learn enough from it. Also, sparsity is another aspect where you can have a regular sparsity in the way you will deploy your models. But on the other hand, you can have more, more kind of a fine-grained sparsity, and you could do your engine in a more specific way. So I think there are two aspects I always look at FPGA. You can always take FPGA as a proof of concept. FPGA has been the world's best emulator. Every iPhone or every Qualcomm phone is first emulated on FPGA, as well as a lot of ideas today you can emulate, but not only emulate, you can today even go and deploy it. So that's not a problem. And again is, people say deep learning, but at the end of the day, you are looking at whole application acceleration. Deep learning is a part of it. So I'll give you an example that we have some customers who have their images stored in the database. And database sits on NVMEs, right? And today what you have to do is you have to extract the database, get all the image, send it to the GPU or CPU, get the data back, get the metadata back, and populate your database. When you're looking at terabytes of data, this is not something very efficient. You spend a lot of time in data movement. But a lot of times you could probably do a lot of these things in line, because on FPGA you can write an NVMe controller, read the data directly, run it through your deep learning engine, and put the data back. And that kind of gives you performance improvement, which is typically not talked about. Most of the time you are talking about compute, but really speaking, at the end of the day, when you are deploying such systems, you are looking at system, the system level performance. And something, I was in a conference attended by TSMC a few weeks back, and a gentleman over there said is, Moore's law will exist, just that it doesn't happen every 2 years, but system performance will continue to improve on a much regular basis, even though Moore's law is not holding. So he went into how to do packaging, this and that, but that was a very interesting talk. So what are the Xilinx building blocks? So I'll come to the middle of it. So when we build the chip, we build a columnar architecture. So you can see that there are columns of particular functions. So there is a DSP function, there is a logic, and all of them are connected by programmable routing, okay? So in principle, if I have to connect this DSP to some VRAM over here, which is our on-chip RAM, you could pretty much have our tools do it in a programmable way. And if you move this from here to here, that thing can be, again, reprogrammed. So reprogrammability is one of the key advantages we have on FPGAs. Again, I would like to say this reprogrammability is not real time. This reprogrammability is basically saying is you can take this FPGA and implement various functions, and if you don't have real-time requirement, you can reuse it for many, many applications. So the core of this is CLB. It's what we call it as a configurable logic block. It has basically what we call it as a lookup tables, 6 input lookup tables, bunch of flip-flops, carry chains to do your arithmetic, as well as muxes for larger logic. And if you go to, maybe I'm sure a lot of you guys already know about it, but if you don't know about it, you can go to Xilinx and learn more about it. So this is a CLB, which does the basic logic. And then there is a programmable routing. And this routing is kind of a hierarchical routing. We have local routes, and then we have long routes. And that's how you basically build the whole chip, okay? Now, for deep learning, one of the biggest thing you do is multiply accumulate. That's one of your core operation. And to enable you to do it, we have a specific tile. We call it DSP48E2. And this keeps on changing with our every version of our devices. So you can see that it can do a lot of things. So it has a 27-bit pre-adder. These two are 18 bits. Then there is a 27 by 18-bit multiplier. It can also do XOR because we play a lot in communication. So CRCs and doing those kind of things is also there. As well as, there is a lot of programmability by which you can implement an operation in single cycle or multi-cycle using the same DSP. From the deep learning point of view, what you could do is you could do basic int 16 by int 16 multiply accumulate in one cycle, or you can do 2 times with int 8, or you can do 4 times with int 4, or you can do 8 times with int 2. Now the thing is that you have to do some logic around it to make all of this thing work. But fundamentally today, with this DSP, what you could do is every cycle you can change whether you are doing int 16 or int 8, int 4, or int 2. Okay? So that is something pretty interesting, because whenever you are talking of quantization of the neural network, what people are saying is not every layer needs to be at int 8. Some layers can be at int 2. Some layers can be int 4. And you can basically design your architecture in such a way that on a cycle-by-cycle basis, you can basically switch what kind of multiply accumulate you want to have. There are white papers over here, 486 and 487, which basically talk more about these two modes. We'll be updating it to talk more about how do you do int 4 and int 2 on the FPGA. Now, this particular DSP block can be cascaded in 2 interesting ways. This is, you can make a big dot product engine using output cascade. There is a dedicated wiring where all of these multiply accumulates can be combined together. Or you could do a 2D array like this, systolic array of accumulators, where at each cross point you put a DSP. So there you can cascade this DSP on the input side as well as output side. And based on how you want to do it, and there is another property this DSP has. When you look at DSP from our chip point of view, each DSP is combined with around 2.5 CLBs. There is basically, so what all you have, when you look at a DSP, along with it, you don't get a BRAM, URAM. These are more macro devices. You get distributed RAM. So what you can do with this distributed RAM is 2 times 16 by 64 by 16 ping pong register files. And this will run at speed with DSP. DSP can run at 800 megahertz, okay? And then there are lookup tables and flops. So what you do is, basically, I'm going back over here, is when you are taking a DSP, you're programming it to do this mode, as well as connecting them in this particular way, what you get is not just DSP, but you get a very fast local memory, which you can use to store your intermediate, to store your weights or some of your data, which is basically reused quite a lot. So if you look at this particular paper, I think it describes what we call it as a supertile, because DSP on its own is just a block, but combined with all of this other thing, we call it as a supertile. And once you have a supertile, what you can really do is you can build really large systolic arrays, right? So on 16 nanometer, we use 3P, which is one of our devices. You can build 112 times 16 supertile arrays, and it can run at a very high speed. This is our -2 and -3. Or 20 nanometer, you could do this. So based on basically what kind of floor plan our device have, the kind of systolic arrays you can build will vary. But fundamentally, these systolic arrays work at the highest speed, do not use any other FPGA logic. And that is something, one of the things we try to use in our DNN architecture. Now, going beyond it, variable precision, compute density. So this is where 8-bit activation and 8-bit weights you can get on VU9P, which is our U200 LVO device. The peak is around 17 teraops. But if you have some fancy algorithm where you can do 1 bit, you can pretty much get 684 teraops or multiply accumulate. Half of that is multiply accumulate every cycle, okay? So really speaking, what you can do is you can, when you are implementing a neural network for inference, you can use all of these capabilities and large amount of compute power which is there on the chip to really design a solution which is really low latency, low power, or whatnot. And I think recently, Professor Han worked with some physicists to do an MLP, which multi-layer perceptron, which could do in nanosecond time, right? So the thing is that is, those are the kind of things which people are trying, which may or may not be even approachable by your standard, GPU architecture. And, just this is my end of talking about FPGAs before I go into our architecture of xDNN. So this is on a VU9P, which is one of our data center chip, which is available on F1. You can see distributed RAM was the LUT RAM, which was sitting next to your DSP. You can get 36 megabit of it, but it's extremely high bandwidth. Then the next level is a block RAM, which gives 77 megabit on this particular device. And then you can see that as you go, the bandwidth keeps on going down. Most of our devices do not have HBM. There is only one device which has HBM, and which just will be released next year. But most of the device, you can build multiple DDR memories based on what you are doing, right? So really speaking, when we say programmable, flexible, these are the kind of things I wanted to share with you, because these are your building blocks with which you will basically build a deep learning, deep learning inference engine. And it's not just limited to deep learning. Deep learning is an example. People are doing cryptocurrency. I cannot say it publicly, but they use FPGAs to do cryptocurrency. Then there are video codecs, all kind of things people are able to do on the FPGA. Okay. So coming to the our xDNN processor. So the way we build xDNN processors, if you look at research, I think we have decided to build our processor different from everything we see. We like to build big systolic arrays, because we know that as soon as you build a big systolic array, you get a lot of bandwidth in moving the data in a particular way, right? So we build a big systolic array, and I'll show you what is the size of the thing. There is a memory for activations, which uses our Ultra RAM and BRAM. So what we do is we try to put as much of memory on chip, activation memory on the chip. And this particular systolic array is an overlay architecture, means it comes with an instruction set and an instruction buffer, so that you are not really programming it as an FPGA. You are basically dealing with it as a higher level ISA, which is similar to the operations you will find in TensorFlow. Then you can see that we do the support operations, and there is a crossbar which connects all of them. And weights are streamed all the time. Because typically what we find is, if you look at the matrix multiplication problem, which a lot of CNN algorithms get into, is basically what you do is you have a lot of reuse on the activation, but when the weights are really coming, you can basically load it in a slower manner, because you load a chunk of weight. You basically do a lot of operations on that, because your activations really are reused quite a lot. And then you move it out to the DDR. So we don't assume everything will be in the memory. Some of that can go to the, if we don't have enough space, it will go to the DDR. It's a 700 megahertz, and I think on a -3 part, we can run this at 800 megahertz. We presented it in Hot Chips this year. And these are the DNN, CNN features which are there. It pretty much gives you everything which is required to do a convolutional neural network. You get convolutions, you get depth-wise convolutions, or deconvolutions, as well as element-wise addition. The precision supported over here is int8 and int16. And you have a variety of sprites which are available over here. So really what we do is we have a compiler, and I'll quickly talk about it a little later, is we read the tensor graph, generate these instructions, push it down to it, this will execute, and that's how a simple CNN overlay, or what they are calling now is a domain-specific architecture, which really we looked at how CNN works and really implement something and made it programmable, so that once you implement it, you don't know how, if you don't know how to play with FPGA, you can still get all the advantages of it. So this is the systolic array in this particular architecture. This is our generation 3. you can see that we have used this addition, like a dot product. The data moves here as well as down. Actually, on the chip, the data moves up. And then you do dot products and you do accumulation. These weights are stored in the local RAM, those 64 times 16-bit, 2 of them which are there. So really, we have 3 levels of memory hierarchy. We basically come from DDR to this, and from this to the distributed RAM, right? So that is really the 3 levels of hierarchy we have. And to really allow simultaneous execution of different blocks, there is this crossbar which basically provides you with a multi-ported memory, which is very specifically designed for this processor by looking at what are the access patterns which are possible, right? So for example, right, it can write to systolic array, simultaneously read from systolic array. It can move data to DDR RAM if this particular thing is overflowing, or for that matter, it can run pooling while it is doing convolution in the systolic array. So these are like, this is again a customized crossbar, and we can tune it for specific requirement. And another thing what we find is, and this is even true for TPU, if you look at TensorBoard and say that I want to target TPU for one particular workload, it will say 70% of the nodes are supported by TPU, or 80% of the nodes are supported by TPU. So typically, we do see that when people write networks, when people write, describe their convolutional neural network, it's not everything is possible to accelerate. So you have to come on going and coming back from CPU or some other acceleration device to do your job. So what we have really implemented to do this is GoTo, right? So basically, the way it will work is FPGA, the CPU will send it to FPGA. When FPGA is done, either it can do an interrupt to the CPU, or basically it could, a CPU can poll and do the next iteration. And the way we do it is, basically we have tried to make data movement as transparent as possible between the CPUs and FPGA. And not only, and I'll go to multi-core, but this paradigm is basically, applicable to not just CPU and FPGA, but also multi-core. And I did talk about instruction level parallelism. The processor does allow you to run convolution while it's doing a bunch of other operations. And typically, the parallelism we build is dependent on the kind of workload. We have a standard architecture, but recently we were working with one customer and they were using ResNet, and the element-wise addition was the bottleneck, and we just built more units for it, and we could do more parallelism over there, okay? And fusing of the operation. So one of the things is when we execute a network, it is completely fused. We do not go back and forth between CPU. You take a network, fuse it, and basically execute as much as possible on the FPGA. And really, this the operation fusing really translate into the pipeline execution in the pipeline we have built on the xDNN processor. So now, xDNN processor on its own is fine. Like it has a systolic array, it has a memory and all that. I want to talk a little bit about when we are basically deploying or when we are basically using FPGA, or especially the big FPGA as an accelerator, we really have nothing like we really have, it's a blank sheet, right? So for what you have to do is to enable FPGA as an accelerator, especially on the PCIe or network mode or whatever, you have to have some logic, which we call it as a shell, which should be basically keep your PCIe alive all the time, because you cannot kill the PCIe. You need to have a way to DMA data between the host and back to the FPGA. And then, so we call this particular region as a shell, okay? And the remaining thing, we call it as a reconfigurable region. So typically what happens is, when we are using FPGA as an accelerator, it is going to take some area away for doing all these support functions. And when you write your application, it is going to basically sit in this reconfiguration area, right? So this is our standard shell, which is, you can see is, when we build the FPGA, this is a VU9P FPGA. There are 3 slices of it, and we have taken half of one of the slice. And the logic it has is, PCI logic, then you have 1 MIG logic as well as DMA logic, right? But for machine learning, we know that we don't need PCI X16, right? We don't need 16 lane of PCI. We are good with 4 lanes of PCI because the data movement is not that much. So we decided to implement ML shell. So the difference between this and that is it gives you more FPGA, and it is more specific to the task what you are doing at hand. So this shell is very important because anytime you will do your application on an FPGA accelerator, you should be aware that some part of the FPGA is not available to you. And this is something when you are using Amazon F1, if some of you might have used, you will see that they take pretty much this much of region for whatever they are doing, right? So how people deploy FPGA in a cloud environment depends on what else they are wanting to do. But fundamentally, you won't have 100% of the FPGA available. But what we are recommending people when you are doing ML kind of application, use a shell which is thinner so that you have most of the other logic available for doing what you are doing, okay? So we basically took the thin shell and implemented 3 copies of xDNN v3 on it. And as I was saying, our systolic array is 96 times 16. So it is 16 columns, 96 long. It's a big systolic array. Runs at 800 megahertz for our -3 part, which is our fastest part. For our nominal part, it will run at 700 megahertz. So at 800 megahertz, what you get is for each of these slices, you get around 5 teraops of peak performance. So when we populate the whole chip, basically you get around 15 teraops. So I said that the peak was for int 8 was around 17. So you're pretty much getting max of it. It's a 2-clock design. Your systolic array runs at 800 megahertz, as well as rest of logic runs at 400 megahertz, okay? And now how you can do it, you can basically deploy the whole FPGA to do deep learning inference, or you can do something more interesting. You can mix and match workload, right? So you could basically do decode processing, run some deep learning, and then basically do video processing, encoding, and send the data back. And it's not just we are saying our customers are trying to use deep learning, not in the standard way. They want to combine it with storage, network, and all the other things as I really talked about earlier. And this is where you talk about system level performance. And that is where we think that we do have a different solution compared to others. And one of the things is anytime you do hardware, we basically say batch of 1, you give it inference, no batching needed. You just give 1 image, you get the data. And you can get a pretty high efficiency. This is one of the GoogleNet V1 efficiency. Whereas for other architecture, you have to batch it up to get to the higher efficiency. And this is the benchmark that was from. So we basically compared a batch of 1 inference, okay? We just said, I want to do batch of 1, lowest latency, what is possible? So today, if you take 4 Tesla V100, it could do around 3,500 images per second. But with our LVO U250 card, you should be able to do 4,200 images per second, batch of 1. All 4 engines running asynchronously. You get a batch of 1, you get the data back. And this is something, the data we have. And you could see that latency is kind of pretty low, right, over here. And really speaking, if you are at a lower batch size, the performance we get is much higher. Surely the GPU does excel as soon as you can batch up the data. But a lot of our customers, even in the data center, as well as this particular solution is being asked by a lot of autonomous drivers who currently are putting 4 to 6 GPUs. They want to say, OK, can we put FPGA? For them, batch of 1 is very important. And you could see that consistently we get a fixed latency, low latency. And at that low latency, we can outperform the best-in-class GPU. And this is a white paper. I'll share this after, or this presentation is. So this is the software. This is the hardware part. On the software side, we have built a pretty elaborate setup. So currently, we do support TensorFlow and Caffe. And MXNet is something in beta. In future, we'll support ONX so that we can take other kind of network outputs. And really, the way we go is we take the tensor graph, convert it into Xilinx tensor graph, do Xilinx tensor graph optimization. The compiler will generate the code. There is an offline quantizer. So you can get quantizer as an offline activity, or someone can do retraining or provide quantization. We have a JSON file. You can give us the format, and we can take it. And then there is an xDNN runtime, which coordinates CPU and FPGA, and this is the whole solution. And it's available for trial on this particular GitHub site. Okay. Now, the compiler is kind of, this is one area where we are seeing is after you have done the architecture, you spend a lot of time writing a compiler. And the kind of things we are currently doing is you have to basically support multiple frameworks. So all kind of readers are being written, reading from MXNet, TensorFlow, or Caffe. Then there are weight extraction and reformatting. When you are doing inference, your weights, you can reformat it in any way, which is very more suitable for your engine. Then DAG optimization, so basically operator fusion is the next step. But the main thing about it is basically it is trying to schedule your instructions so that most of the time you can use the on-chip activation memory for your computation, okay? And this is really the core part of the compiler. Now, so there are really two parts to it. One is tiling. You're not always going to, so when you look at machine learning, typically the standard academic benchmark use 224 by 224 images, right? They're very small images, and all the benchmarks are published on it. In real life, people are basically saying, hey, can I process 1K image? Can I process 2K image? We have customers who want to directly process 4K images. So what really happens is you cannot really process the whole image because you cannot load it. So there has to be a tiling which you have to do. And that tiling is not just applicable to the first layer. It is pretty much applicable to all the layers over here, right? So this is one of the area where we spend a lot of time so that we reduce the data movement between DDR and on-chip RAM. And this is somewhere where HBMs do help, but HBMs have an impact on cost and some of the other things. And this is another example. I may not go into the detail. Like let us say take the GoogleNet, it is going through these multiple steps. So what it is really doing is at each stage there is an activation input, you do an operation, and you write an activation output. And this is an example of one of the ways the compiler can schedule the job, right? It can start with 1 by 1, and then 3 by 3, which is the next, can use the result of 1 by 1, will give you the results over here, and so on and so forth. The big thing is that whenever it is possible that you can fit your activation in on-chip memory, this is kind of gives you the best of the latency. And this is an example of a real compilation for GoogleNet V1. So you could see that I can say for my convolution engine, I just give 2 megabyte of on-chip RAM, okay? Or I can say I give you 5 megabit of on-chip RAM. So GoogleNet, we know if you are giving 5 megabyte of on-chip RAM, pretty much the operations you are doing is convolution, max pool convolution, there's nothing happening. But as soon as you give it a less amount of memory, what you have to do is this scatter and gather, you are seeing you have to start moving data in and out to the DDR. Here HBM helps, but fundamentally the problem is the more you can fit on the chip, the better it is. And that is why some of the work on quantization, reducing the weight, reducing the activation, basically allows you to get more to this, because if you do more of this versus the top level one, you kind of have a lower latency as well as you have a lower power, okay? And for the quantization flow, it is pretty standard. What we have is we basically calculate thresholds in two ways, using an offline method or using retraining. And this is something what we do is from the sample data set you have, we'll basically draw, or we will calculate the statistical probability distribution graph you have. And typically what you are really saying is, let us say, look at this particular graph. most of the important information is basically at this activation level. After that, it is not, like you can drop it. And typically, this is the thresholding we do. And once we do the thresholding, we do a linear quantization. Basically, take that range and map it onto the 8-bit or 16-bit, depending on that, right? And this is some of the examples. If you go to our public website, this technique is available. ResNet, if you just quantize it, don't do anything, you get this. But if you do a little bit of retraining on top of it, where you are running those weights, what you generated by step 1, and run few iterations of HGD, you kind of get a better accuracy. But overall, this is a proven method, and this is something which works for most of the things which are out there. And to make it easy to use, we wrapped up the whole of this FPGA or our DNN engine in Python. You really don't have to know. Today, you can go to Xilinx. I'll show you the website. You can basically write your workflow just simply as simple Python code. So here, I'm executing xDNN in the blocking mode. I'm preparing, executing, collecting the data, doing something on the CPU. Here, I'm saying is, OK, I will execute it asynchronously instead of synchronously. And here, basically, I'm saying, OK, I have 8 FPGAs on the system. Let's try to scale out on that, OK? And this is really, you go to github.com, Xilinx ML Suite, whatever I am talking is available, including the binary. If you get access to the board or your F1 account or a Nimbix account, you can basically try this. And there is a notebook support over there, so that if you don't want to go deeper into it, you can do most of the work using our predefined notebook. And some of our customers who have data scientists in their group are basically programming that using the notebooks. And this is something I want to share. This fun project, we did it recently. We have basically heard a lot about EPIC system from AMD. It has the largest number of PCIe lanes available for the external compute. So what we could do is we could basically put 8 LVO cards, 250, LVO 250. And what we really did is we just did a scale out of this. We used 250, and we could get pretty much, by writing simple Python scripts on the top, around 30,000 frames per second of GoogleNet V1. Now, this particular platform is really interesting. Now, this is an interesting result from the point of view of batch 1. You can get high throughput. There is so much of data being looked into. I think this is interesting. But one thing is that if you really count the total number of lookup tables, it is basically more than around 10 million lookup tables. And 12,000 times 8, those many, around 100,000 DSPs. And given that these are connected to the CPU in an interesting way, and AMD is pushing for that, you can really build more complicated data flow. Deep learning is one part, but if you want to do something else, get the data from somewhere, you want to do some pre-processing, do it. All of this can be done, and all of this can be done in a reasonably straightforward way, OK? So fundamentally, I just presented an architecture where no FPGA expertise is needed. Compile and run trained networks, but also I kind of got a little bit deeper into how we implemented all of this. You can deploy it on AWS and other cloud platform and deploy in PCIe card. And this is my last slide. This is our next generation of FPGA. Currently, our FPGAs are built with 16 nanometer. The next generation is built using 7 nanometer. And this overlay systolic array concept, what we did is we just went ahead and hardened it. So today, if you look at our Versal chips, if you look at the biggest chip, which will come out sometime next year, it will have 110 teraops of int8 performance. But the key for us is not just that. It's basically it just provides a lot of other support functionality, where again, now using this particular device, you can really attack whole system level compute acceleration, where deep learning is an important part of it. So thank you.
Thanks, Ashish, for the great talk. We have time for some questions. Yeah. 1 or 2 questions.
Yeah.
I was impressed with your one slide which showed that your example of running an application was 3 times The reputation of FPGAs is they're more power hungry. So how do you explain the fact that, what were the inefficiencies that caused that comparison to play out?
So one of the things is that is, and this is a general thing, right, is if you are moving, see, if you really look at, if you profile your power, there is a power on the compute. But on the other hand, there is enough power which goes when you are going in and out of DDR, right? So we do see that, I do think that one of the big reasons why NVIDIA can have more power is just because they are using high bandwidth memory. But on the other hand, this is typically the case of dark silicon, and again, I do not know. It's basically, I think if you really look at how NVIDIA executes this engine, it is basically doing a multi-threading SIMT kind of thing where they're moving data in and out. And you basically load up the FPGA, load up the GPU with enough threads so that it is busy most of the time. So from that point of view, I'm sure that they have put in enough logic, which is just taking care of fast data movement, scheduling, and other things which may or may not be working on compute. But for us, fundamentally, number one is we are doing integer arithmetic, which has an advantage for us. We are using a lot of on-chip memory, and as well as we have customized our processor to a specific problem in hand. So I think I would just say that these are the few areas which may show the difference. But FPGAs typically never go beyond 100 watts. Like typically most of the applications in FPGA go 50, 60 watts. And we have seen crypto applications or high speed like 400 gig networking and all that. The max I have seen is around 110 watts. So it's just that the fabric is fairly efficient. Yeah.
Can you make a comment on what the power will be on this, your new part in terms of teraops per watt or something? Or
Yes. So I think it will get better because of this particular AI core. And I think today, I think we can get, somewhere around, I don't exactly have the numbers, but I think we should be able to get around between like 2 to 4 teraops per watt. I have to go and look at the spec sheet. But currently we are, I think it is around 4x advantage versus what we have now. And the reason is that again, we are not providing a programmable processor. We are basically providing a processor which will hook it up based on your application. And I think that once you remove that dynamic property, I think you do get a power advantage of that. Yeah.
All right. Any more questions? All right. Let's thank again Ashish for the great talk.
Thank you.
And we are happy to talk with you offline as well.
Yeah. Thank you.